also put it in wording later on in our Green Learn announcement. So for example, your final exam covers from chapter 1 to chapter 7.3, the Clapeyron equation. Your final exam will be the same length as your midterm 1 plus midterm 2. So you know how many problems to expect, right? You have 3 hours to finish an exam that's your midterm 1 plus midterm 2. So hopefully this time we will for sure have enough time for you to finish everything. Your TA will also still host review session and tutorial session this week, even if we do not have any new discussion worksheet, just for you to practice more problems with you. What else? Wednesday and Friday, so we will spend one day working on review of the subject and see how they actually connect with each other. So again, at the end of the quarter, I want you to have a comprehensive understanding in why do we care about thermodynamics. And the other lecture will be a practice problem together that will have one part just do multiple choice and true and false and how to do it quickly and accurately, and one comprehensive problem that uses like different section of your knowledge. So raise your hand if you want to see my review on Wednesday and then practice problem on Friday. Okay, so raise your hand if you want to see my practice problem on Wednesday and review on Friday. Okay, I know what to do then. All right, and with that in hand, do we have any questions on the administrative end? I'll put everything I just said in wording later today, so you know that on paper. All right, one more little thing about like curving of this class. So right now our class average is about 81%. So that is still within the B- range. So if after the final exam, our average falls below 80%, which is a B-, we'll curve everyone's grade up. But whatever we do, it's only gonna help your grade. It's never gonna damage your grade. All right, any other questions? No? Okay, so I have office hour tomorrow. That's gonna be my last office hour. If you have any questions, just please come by and just have a final chat about your grade or your standing in the class. That's also fine. We can also find some privacy in my office hour. Okay, so get back to our lecture today. So chapter 7 talks about the phase diagram. So a few things we discussed last Friday and also last Wednesday. So we started by introducing the concept of degree of freedom. So for example, if we think about the triple point and you use the degree of freedom to calculate the degree of freedom at your triple point, you have F equals to the component minus phase plus 2, right? So C is the number of components we're talking about. P is the number of phases that are in equilibrium with each other. And that 2 degrees of freedom stands for temperature and pressure. So at the triple point, for a one component system, we have degree of freedom equals to 0. So 1 minus 3 plus 2, that equals to 0. So that tells us for any pure component, we only have one triple point. So basically that's an iconic character of that specific chemical species we're talking about. All right, so for example, for any water, when we talk about water as a component, now the triple point of water will always be the same, no matter where you are, no matter what's the pressure or temperature we're talking about. The triple point where your liquid, solid, and gas are in equilibrium with each other will only have one number. So that's where that 0 degree of freedom comes from. So last lecture, I believe Dr. Kovner went over carefully with you in how to read the one component phase diagram. So let's just quickly review some of the key points on a one component phase diagram. So for example, in this case, we have solid, gas, and liquid. And just think about the qualitative understanding about where you expect your component to be solid, right? When the pressure is relatively high and your temperature is relatively low, right? Likewise, when you expect that component to be gas phase, we're talking about higher temperature, like you boil water at higher temperature, and relatively low pressure. And liquid is sort of in between. And these lines that separate your gas phase, liquid phase, and solid phase. These are lines that separating your two phases. All right, so for example, if we use this line here, the AD line, so this one is your melting point line. So what we have is solid, liquid, equilibrium. So if we're plugging back to our degree of freedom, we still have only one component, but now we only have two phases that are in equilibrium with each other, -2 plus 2. So we have 1 degree of freedom. All right. And likewise, for example, this line here, the OA line, this one is obviously your gas solid equilibrium line. So along this line, your gas and solid are in equilibrium with each other. And here your AC line, that's your liquid gas equilibrium point. There's one more point that's interesting on this curve. But before we do that, let's think about what is the qualitative understanding you can get by reading a phase diagram. So for example, if we have a tank of gas, now we want to have the liquid form of that gas, right? So here we're just using water as an example. We have a tank full of gas phase water vapor, and we want to somehow condense that water back into your liquid phase. So what you can do, so we start from some kind of gas phase here. There are two different ways you can do. You can either keep your pressure relatively constant, and then by decreasing the temperature, you get it back to the liquid phase. Or you can keep the temperature constant, and by adding more pressure, you can condense that water back to liquid phase, or it's called the isothermal compression of gas. All right, so that's how you qualitatively read a phase diagram. So for example, in a multiple choice question, let's just as an example, right? I can put a point here, like a solid, and a point here that is liquid. And we ask you what describes this process. You can say that it's isobaric increase of temperature and choose from like a bunch of options, right? So that's just an example question. Now, back to this point here, this point C is what we call a critical point. So the meaning of critical point basically means beyond the critical point, so all the area above that point C, that tells you your gas and liquid are basically undistinguishable with each other. So they're like coexistent. Or your the density of your gas is so big, it's almost like a liquid, but it's not a real liquid. So it's like a stable phase. So what's the physical meaning of that beyond critical point area? Now, if you think about it, for example, if I start here, if I start my gas point here, and no matter how I increase my pressure, I'm always in this like beyond critical point area. So no matter how large I increase my pressure to, I can never liquefy my water vapor back into liquid water. So that's the physical meaning of that critical point. All right. Or the more scientific way to put it is that beyond the critical point, isothermal compression of the gas does not lead to liquidify. All right, so now let's look at a specific process and try to give that specific process a little bit more chemical meaning by plotting your Gibbs free energy or your chemical potential versus pressure in this case. Now, the specific process we're talking about is between your R to S to Y point. All right, so from now, we're going to use our thermodynamic knowledge of the system to try to come up with a plot from your phase diagram that's talking about the correlation between your Gibbs free energy or your molar Gibbs free energy or your chemical potential versus pressure at constant temperature. So if you're in the classroom, we're fine, but if you're watching the recording, try it yourself. So this is the graph to start with. The molar Gibbs free energy versus pressure at constant temperature. All right. So let's think about this process. So first of all, we want to look at the point R here. Or let's look at this process between R to S in gas phase, and between S to Y, this one is in liquid phase. Let's just write out what do we know in this problem and how do you approach this kind of problem. So that's a plot we're aiming for. Some of the things we know, we're talking about the change in Gibbs free energy. So we have Eg equals to negative S dt plus V dP. So when we're talking about constant temperature process, this term goes to 0 at constant temperature. So what do we have is your dG equals to VdP. Or if you remember what Professor Comner showed you, is you're expecting a somewhat increasing slope. But what exactly is that? Is that line? What is the mathematical representation of that line? We actually have enough tool to solve that question. So bear with me a little bit. We're talking about the transformation between R to S, so that is a gas phase process. All right, so what do we know about the gas phase? We have dG equals to V dP. Now let's assume we have ideal gas. Having real gas just make this calculus more complicated, but not necessarily changing the general shape of your mathematical representation. So let's just assume ideal gas for now, just to keep ourselves happy. What do we know if we assume it is ideal gas? What we should be using when we have ideal gas, obviously we have PV equals to nRT. So how can we further simplify this equation here? Right, so we can write in volume to be nRT over P dP. All right, taking the integration of both ends of this equation, what we have is your G equals to nRT, integral of dP, that's your nRT log P. All right, and some constant, let's just not worry about that constant there. All right, so that's just solving what we know using the ideal gas law. So what does that mean? That means when we're plotting this equation, we're plotting Gibbs free energy, or Gm here. I believe it's N. So when we plot your molar Gibbs free energy or your potential, chemical potential versus pressure, we're looking for a logarithm function. All right, so if we plot it on here, let's just put a random start point at R, which is at a relatively low pressure. The increase of your molar Gibbs free energy with respect to pressure is a logarithm function, or a natural log function. So it's something look like this, until it reaches that equilibrium point S. So this part, we have our gas phase, and we're just approximating using the ideal gas law. And your Gm is roughly equals to what we have there, which is RT ln P. plus some constant C. All right, so that's where that logarithm function comes from. Now that's a gas phase from R to S. What about the at equilibrium? What is going to happen? What kind of property do we expect to happen at equilibrium where you have only one component that undergoes phase transfer? So some of the things we know that will be equal at equilibrium. For example, we expect the molar Gibbs free energy to be equal to each other, and the change of your molar Gibbs free energy also equal to each other at equilibrium. All right, so at S, so this is my gas phase. And then at equilibrium, which is my point S, what we have is your Gibbs free energy of gas equals to your molar Gibbs free energy of liquid. Also the differential of your molar Gibbs free energy at gas phase and differential of your molar Gibbs free energy at liquid phase, they're equal. You can also replace that GM with chemical potential. For one component, they're just by definition the same thing. So back to that plot, what do we know about that? So at this point, which is my gas, liquid, equilibrium point. So we have the dGm gas phase equals to dGm liquid phase. So this one, let me just annotate it with gas phase. So that tells us if we're looking at the slope of my gas phase curve, and you find the slope at this point C, you sort of extend it. All right, so the slope of your new equation for your liquid phase molar Gibbs free energy need to be the same as the slope of your gas phase molar Gibbs free energy. So what do we know about the liquid phase? Now again, we're using the same equation. We have dG equals to VdP. Now in this equation, we're talking about how your volume is going to change with respect to pressure in the liquid phase. So one of the easy hypothesis to make is your volume is not going to change a lot with respect to pressure if we're talking about a liquid. All right, so this one, because we're talking about liquid, we can roughly say volume is not changing with respect to pressure. It's an approximation, but it is like a reasonable approximation we're making to plot that figure. All right. So with that in hand, what we can write is your Gm, the molar Gibbs free energy of your liquid, is roughly equals to, where this roughly comes from, we assume the liquid volume is not changing with respect to pressure. So this will roughly equals to volume times pressure plus some constant. We don't care what that constant is, just a constant. And you can just solve this by taking the integral on both ends. So what does that tell us? So that tells us in this case, we're looking for almost a straight line. Not very good at drawing straight line, but you get the gesture. So this is the liquid phase, Gm, liquid. That's roughly V times P plus some constant C prime. All right, so that's how we use whatever we learned before, nothing fancy, a little bit of calculus and our ideal gas law to plot how your molar Gibbs free energy is going to change with respect to pressure. All right. And just to make one more connection to whatever we just derived to what we know. Now we know the slope here as volume. So if you remember our Gibbs equation, we have volume equals to the partial derivative of G over P at constant T. And it is the slope of our partial derivative of Gibbs free energy. Well, in this case, it's a normal derivative because we're keeping T constant. So it is a normal derivative of your Gibbs free energy over the change of your pressure, just to make another link between the volume here. Any questions? It's still a relatively qualitative picture of the phase diagram. One of the problems you could expect, we can ask is, for example, instead of your gas to solid, we have this kind of gas to liquid, we have this kind of transformation, and you can, we give you 3 points, right? Create a similar kind of figure, assuming your gas is ideal, and so on. All right, any questions? We're good? Okay, sounds good. Next up, the Clapeyron equation. So this one is the more quantitative picture of the phase diagram. So whatever we just went over is a more qualitative picture of the phase diagram. How do you use the phase diagram to plot that delta G versus P? Not without doing any real calculation. Or how do you generalize qualitative description about what kind of event is taking place in that phase diagram, in a specific transformation. So now let's look at the more quantitative picture of the phase diagram and use the Clapeyron equation to actually solve for specific things on your phase diagram. So I'll give you the equation first, which is, here is the Clapeyron equation. And we will first go over the derivative of the Clapeyron equation and see how we can use the Clapeyron equation to solve for properties on your phase diagram. All right, so 2 different steps. Let's get started with the derivation. So the idea here is simple. When we're defining the Clapeyron equation, what are we talking about? We're talking about how your pressure is changing with respect to temperature. Or on the phase diagram, right? The phase diagram on the y-axis, you have your pressure. On the x-axis, you have your temperature. So this is just a zoom out version of your phase diagram. We're saying this line represents the equilibrium line between 2 different phases. Now, these 2 different phases can be liquid, solid, can be liquid gas, or even solid. So just 2 random gas, 2 random phase between phase alpha and phase beta. So in this case, what do we have? The first thing we know is that at equilibrium, like what we just used here, we have the Gibbs free energy of your species in phase alpha equals to your Gibbs free energy in phase beta. Now, let me just specify your point 1 here. So this 1 doesn't mean a different component. It just means that point 1 on the figure here. All right. Or you could also write this as your chemical potential alpha equals to chemical potential of phase beta, where your chemical potential just equals to the molar Gibbs free energy. That's the first step. Second step, express this point 2 here using what we know about point 1. So this is also pretty straightforward, right? So your molar Gibbs free energy at point 2 in phase alpha equals to the molar Gibbs free energy in point 1 at phase alpha plus the change dg, or infinitesimal change dg in phase alpha. All right, so dg is what we have. That's the difference between your point 1 and point 2. And likewise, you can do the same. For phase beta, you have the molar Gibbs free energy for point 2 equals to the molar Gibbs free energy in phase beta at point 1 plus dgm for your phase beta. Nothing fancy, we're just expressing what's the chemical potential at point 2 using that infinitesimal change and the molar Gibbs free energy or chemical potential at point 1. And also at point 2, at the same time of this expression, we have that the molar Gibbs free energy or chemical potential in phase 2 equals to that molar Gibbs free energy in phase beta at point 2. All right, so these two you can just write out because they're on that equilibrium curve. So, and what we know that your G alpha M2 equals to your G alpha M1 plus DGM alpha. And this one is here. So we can write these two to be equal to each other. All right, just different expression of your molar Gibbs free energy at point 2. And since we know the molar Gibbs free energy at point 1 for phase alpha and phase beta are equal to each other, so these terms will cancel out because they're equal to each other. The expression we end up getting, let me just move it there to have enough room. The expression we end up getting is your D, the infinitesimal change of your molar Gibbs free energy of phase alpha equals to dg, the molar Gibbs free energy, infinitesimal molar molar Gibbs free energy in phase alpha and phase beta are same to each other. Nothing fancy, just moving the terms a little bit. And then we're gonna start using our thermodynamics. So what do we know? Now we have our Gibbs equation. So your dg equals negative SDT plus VdP. So your dgm, the molar Gibbs free energy in general, equals to negative molar entropy dt plus molar volume dP. All right, so a few things here. Now, your molar Gibbs free energy, that's an intensive property. Your Gibbs free energy is an extensive property, just to make sure you don't confuse yourself. So in this case, your molar entropy, that is intensive. It is independent from the size of your system. But entropy itself is extensive. All right, so intensive, the intensive property just means no matter how many of that molecule we have in the system, they all remain the same. Like volume. Volume is more straightforward to understand, right? You can have a 1 liter of water versus 20 liter of water. So volume is extensive, but molar volume is intensive. Just a quick check, because I think lots of people miss that in the second midterm exam. All right, next up. We're just plugging this expression of your Gibbs free energy into here. What do we have? Well, just plugging, we have negative molar entropy in phase alpha dt plus molar volume dP in phase alpha. That equals to, on the right-hand side, we have phase beta. So negative molar entropy in phase beta dt plus molar entropy phase beta dP. So we can move the term a little bit so that my volume stays with my volume and my entropy stays with my entropy. So that's, we have Vm alpha minus Vm beta dP equals to your molar entropy alpha minus molar entropy beta dt. This is just moving terms. Remember, what we want to derive is your dP over dt, or how your pressure change with respect to temperature on your one component phase diagram. The next step, obviously, is moving the term. So we have dP over dt equals to the molar entropy of alpha minus molar entropy of beta over molar volume of alpha minus molar volume of beta. Or when we have this kind of expression, what we are talking about is the change of your molar entropy when you're having the phase exchange between alpha to beta. And on the bottom, we have the change of your molar volume. Right. And we derived this a pretty long time ago, that reversible phase change. So this one is in 3.25. We did that derivation to have delta S equals to delta H over T. So if you don't remember how that's being done, I highly recommend you go back to chapter 3 and review that derivation in y delta S equals to delta H over T. But it's actually pretty straightforward because your S is defined to be the Q reversible, right? And for a reversible process in this case, you have QP equals to delta H for that constant pressure reversible process. Nevertheless, so if you don't remember how that's being done, you can go back to chapter 3 and do that quick review. So our final result is what we want. We have dP over dt equals to delta H, the molar enthalpy, over T times delta Vm. Now you can also write it as the extensive version. So delta H over T delta V for one component, two-phase diagram, two-phase equilibrium. All right. And the reason we can do that intensive version and the extensive version is you can have the number of more cancel out. Like your delta H equals to delta HM times N, and your delta V equals to delta Vm times N. Since we're talking about closed system without exchange of your material, then the total number of more will always remain the same. All right. So that's a derivation of our Clapeyron equation. Again, what our Clapeyron equation does is it describes how your pressure change with respect to temperature for a one-component two-phase equilibrium in a closed system, presumably. All right, so that's the derivation. And then we'll see two examples of the Clapeyron equation and see how we can use it to solve for some more quantitative picture in our phase diagram. So the first application is our liquid vapor or solid vapor equilibrium. So liquid vapor, solid vapor, they're similar to each other, so we put them in the same box. And later on, we'll look at the solid-liquid equilibrium. We'll save the solid-solid equilibrium because we're not talking about the higher order phase diagram. So liquid vapor and solid vapor equilibrium. Again, this is our Clapeyron equation we just looked at. And there are several approximations we will be using to simplify our Clapeyron equation so it's easier for us to calculate mathematically. All right, so the Clapeyron equation is more generally true, but we are going to introduce some approximation into the Clapeyron equation. So when we're using the Clapeyron equation, we introduced some system-specific approximations. So keep an eye on these approximations because they might fail. And when they fail, you shouldn't be using the Clapeyron equation. So let's look at it. The first approximation we're making is the volume of your gas is going to be way larger than your molar volume of a liquid or the molar volume of a solid. So that's our approximation 1. All right, so molar volume of your gas is way larger than your molar volume of liquid or solid. So beyond the critical point, or even close to the critical point, where your gas and liquid are pretty much behaving like similarly to each other, then this approximation doesn't hold. And also the second approximation, that we are saying where approximate gases behave ideally. So both approximation 1 and 2 will fail when we approach the critical point where your gas become more dense, more like a liquid. So know these approximation and know that if we're approaching the critical point, we shouldn't be using these kind of calculations. Now, with this approximation, what do we have? If we know the molar volume of your gas is way larger than your molar volume of your liquid or solid, what we can approximate is the change of your molar volume if we're talking about a process that's going from a liquid or solid to a gas phase. Then your delta Vm of that process is roughly equal to the Vm of the gas. So this one should be pretty straightforward and intuitive. And next one, because we are approximating the gas behave ideally, so we're using the ideal gas law again. So PV equals nRT. Take over that N here. You have your Vm, the molar volume of your gas, equals to RT over P. So these are the two equations we're using to get to this expression. Then what do we know using our Clapeyron equation? So this is the original form of our Clapeyron equation. We have dP over dt, roughly delta H molar enthalpy over T times the change of your molar volume. So in this case, we can rewrite this one as like delta Hm over T times pressure times RT. So this is just writing our delta Vm. Into this expression. Right. So just using our two approximation to rewrite our dP over dt into this form, where it's P times delta Hm over RT squared. Next, we're going to use a little bit of calculus. So what we have is a differential of your 1 over T over dt equals to negative T squared, 1 over T squared. And your differential of ln P will equal over dP will equals to 1 over P. So a few of the things we have is, let's put our P times D ln P. So my P times D ln P equals to dP over negative T squared D1 over T equals to dt. Or let me just finish, dP over dt. So in here, your dP equals to P times D ln P, and your dt equals to negative T squared D1 over T. That's where we come from. That's the calculus part. And on the right-hand side, what do we have? We have this, right? So that equals to P delta Hm over RT squared. some of the terms cancel out on both ends of the equation. So you have P and, oh, that's a white one. So you have P and P cancel out, T squared and T squared cancel out. So our final expression is D ln P over D 1 over T. That's roughly equals to negative delta HM over R. So remember, what are the approximation we're using? We're talking about solid or liquid to gas equilibrium. That's one. Secondly, we're assuming the volume, the molar volume of your gas is way larger than the molar volume of your gas, of your liquid or solids. Thirdly, we're approximating our gas is behaving ideally. All right, so know what are the approximation we're using here. So for example, if I give you this expression and say, hey, is it still true near the critical point? Or is it generally true no matter where we have on the phase diagram? Then it will be a false answer to that statement. So whenever you read a statement, just make sure you know what are the approximation we have. All right. Next step, how do we use it? Well, then it becomes quite straightforward. You're just taking integration on both ends. Well, reorganize the term and taking the integration. So we have D ln P is roughly equals to delta HM over R D 1 over T. And if you take the integration on both ends, we have ln P2 over P1 roughly equals to negative delta HM over R over 1 over T2 minus 1 over T1. So in here, we make another assumption that our delta HM is relatively independent from my temperature. So we can't looking at very big temperature changes neither. So when we see relatively small, like 20 Kelvin, it's pretty good. But if we look at 3,000 Kelvin, then it's probably not a good approximation. Or this is my approximation 3, that delta HM is constant along equilibrium line. All right, so we start from the general form of the Clapeyron equation. We went over the derivation of the Clapeyron equation. And then looking at a specific problem, which is solid to gas or liquid to gas equilibrium transformation, we derived a more easy to use form of the Clapeyron equation with 3 different approximations we made. And then we're ready to solve problems using this equation. But again, keep in mind what are the approximation we're making here. All right, so let's look at one example problem here. And I'm gonna go over some of my generalized problem-solving tools with you. So for example, let's read the question. The normal boiling point of bromine is 58.8 degrees Celsius. Its vapor pressure at 25 degrees Celsius is 0.2870 bar. It asks us to estimate the average vaporization enthalpy, molar vaporization enthalpy of bromine in this temperature range. So what do we have here effectively in this question? Now, in this problem, it's very useful if you actually plot that pressure versus temperature and plot whatever we know into that figure. Right, so what do we know? At the initial point, we have, well, at P1, we have your vapor pressure at 25 degrees Celsius is 0.2870 bar. So your P1 equals to 0.287 bar, and your T1 equals to 25 degrees Celsius. So that's one of the points that's given on my pressure versus temperature plot. Next up, the normal boiling point is 58.8. So it doesn't give you the pressure, but it says the normal boiling point. So that expects you to know a normal boiling point means that at this point, at boiling point, your P, normal boiling point, equals to 1 atm, and your T, boiling point, equals to 58.8 degrees Celsius. All right, so that means if we put these two plots here, we have that's my P1. So your T1 is 25 degrees Celsius, your P1 is 0.287 bar. And at boiling point, you have temperature at boiling point equals to 58.8 degrees Celsius, and your boiling point equals to 1 atm. So obviously, there are things you need to do before you actually plug in that into our simplified Clapeyron equation. Like you need to get the pressure unit consistent, you need to transfer that temperature into Kelvin. But nevertheless, let's just write out the equation we'll be using. That's our Clapeyron equation. That's our ln P2 over P1 roughly equals to negative delta Hm over R T2, 1 over T2 minus 1 over T1. And here, this delta Hm is what we're looking for in that original equation. So that's defining the problem using whatever we know. All right, that's the first step of any problem solving. Second step is pull all the constant and equations you need. Now we have our equation, and let's put our necessary unit and constant. We need our expression of R, so that's 8.314 joule per Kelvin per mole. So the reason we have to transfer our temperature into Kelvin is that in your gas constant, you have Kelvin in there. So without that transformation, that unit does not cancel out. So we have to transfer our temperature, T1 equals to 25 plus 273.15 gives you 298.15 Kelvin. T2 equals to, well, you can do the calculation, 331.95 Kelvin. So again, the reason we have to transfer it is because we want these units to match up with each other. Likewise, for pressure, it doesn't matter which one you transfer to, just make sure the unit is the same because you have P2 over P1, right? So naturally you want them to cancel out with each other. So here we'll just write P1 equals to 0.287 bar, which is 0.283 atm. So my P2 can, or P boiling point, can stay as 1 atm. And then we're ready to plug in the number. All right, so again, the whole point here is for you to not losing point unnecessarily in setting up your calculation, because you need to keep in mind whenever you divide two things together, they must have the same unit. And then the calculation part should be quite straightforward. We have logarithm of, let me just copy this down. We have the natural log of P2 over P1 your P2 is 1 ATM over 0.283 ATM. That equals to negative delta HM over R, which is 8.314 joule per Kelvin per mole, times 1 over T2, 331.95 Kelvin, minus 1 over T1. Right. You can plug in the number yourself, but in this case, just make sure your unit cancel out. And then you can plug in the calculator and find our results. So that's a general approach I take to set up a problem. We will see more example next lecture. I think I'm running out of time. We'll see one more example on the solid liquid versus gas equilibrium. One more, and then we went over the solid liquid equilibrium and see one more example on that domain. And next lecture, we said you want me to do the summary first, right? Okay, so next lecture, once we finish that, we'll do a entire quarter summary and see how things link together. And on Friday, we will have a practice on 2 sets of problems, multiple choice and a comprehensive problem. All right, and I think the quarter end evaluation is open on my UCLA, so fill it up if you have the time for it. And that's all from me.